Okay, we continue with a little bit more gas theory. We are searching for what is called then the isentropic relations. So it's sort of how far can we go, say, with pen and paper. And yes, we're going to need these. So isentropic relations. And we looked at an example last week. Then we had the following situation: something flowing inside, hitting, say, an object. And then, yeah, you had a nice flow around it. And then we had one streamline hitting the stagnation point. So I used that one as an example. And then actually I used Bernoulli, compressible Bernoulli, that is. And yeah, we had some relations then between whatever we had here. We had a velocity infinity, temperature infinity, pressure infinity, and then find the corresponding values in the stagnation points. So I'm going to reuse sort of the results from that case, but we change sort of the situation here. We're going to look at the following. Here I have an area, call it stagnation. And inside there you will then have, of course, you have zero velocity. It's a stagnation area. But you have some surrounding temperature and some surrounding pressure. If you want to call them infinity, be my guest. Just a name anyway. And then you go from this stagnation area into a local point in our flow. A local point, and inside here we will then have a velocity, and we will have a temperature, and yes, we will have a pressure, and also a density if you like. Something like that. And we are going also to use the adiabatic relations. Adiabatic states that the pressure over P0 over P can now be written as the density in the stagnation area versus the local point to the power of gamma. And gamma for air, what is it, 1.4 or something like that. So I'm going to use that one. And also, yes, we are using the ideal gas law, saying that pressure equals the density, gas constant, and the temperature. We need that one to close our equation system. And then the solution that we had last time can actually be used for this setup here. Exactly the same relations. So we will have the following equation system then. T0 by T. It will then can be written then as 1, and then it was gamma minus 1/2 Mach number square. So that was temperature. We had the density, and then that one should be written as 1 plus, and then the same gamma minus 1/2 Mach number square, but that one is raised to the power of 1 divided by gamma minus 1. Something like that. And then finally the pressure. P0 over P equals 1 plus, and then the same here, gamma minus 1/2 Mach square. And this one was then raised to the power of gamma divided by gamma minus 1. So there you have the simple isotropic relations. And to achieve them, yes, we still have this assumptions that we have done. So yes, it's adiabatic, and also it's no viscosity. So meaning it's reversible, and then yes, the entropy is going to be constant when you do it as easy as this one. So that's fair enough. Okay. So now we can play around with these relations and get a connection then from a stagnation area to a local point inside our flow. That should be now possible. What else do we need? Do we need that one? Yeah, we need that one as well. So not only temperature, pressure, we should actually add a density here as well. Density. And then actually the speed of sound is going to change. What's the speed of sound? Speed of sound, that was A, and it was the square root of gamma RT. So when the temperature is changing, okay, then the speed of sound is going to change as well. So actually we could have included that one as well. So an A0 here, and then just an A here as well. So everything is changing. Everything is changing, or everything may change. And that means also, if you look at, say, for instance, here, that one, he will then imply something like this. T0 over T can actually be written as A0 squared over A squared. So we can have that one as well. Now I want to look at some the critical values here. When the Mach number is 1, then we have the sonic situation, and as we saw earlier, in a convergent divergent nozzle, that can only happen in the most narrow cross-sectional area. So what happens there when we have Mach number 1? Yeah, we don't need this. So these values, Mach number 1, we call them critical. Critical values. For Mach number 1, meaning it's sonic, something like that. And yeah, if you now just punch in the numbers, gamma is say 1.4 for air. If you have different gas, then you have a different number there. I have to look it up. So what will we then have? The critical values. Denote them by star. So then we'll have T star by T0. Yeah. I wonder if I did something wrong here. I think the 0 should be below here. I think it should be like this. Yeah, I'll just do 1 over if you like. So then, if you insert the numbers here, what do we have? Well, this one, 0.833, and so on. Critical density will then be 0.634, and then the pressure P0 equals 0.528, something like that. You see these values, they change a lot. They change a lot. Okay, so far so good. Now we go back to our nozzle. So now we have all these critical values. We know where this is going to happen when we have this geometry, a convergent divergent nozzle. We have these relations that can calculate them. But remember here, the entropy is constant. It's a reversible setup here when we don't have any viscosity, and we treat everything as adiabatic. This is not true when you pass a shock wave. So they are limited. You can't go beyond the Mach 1 here. Then the theory that we have done so far breaks down. Okay. Let's go back then to our geometry and then have some scenarios there. So we have a convergent, divergent nozzle, also called a Laval nozzle if you like. So here is our nice little geometry, something like that. And we have then to the left here, say I have a reservoir or something. Reservoir. So I have an area here, which then is very, very big indeed. Infinity. And then, yes, you have a pressure here, and you have the velocity here is going to be 0. You have a density, temperature, whatever you want. Something like that. Here, the narrowest cross-section, here. Then I have my area sub m. Then we know that is where we can achieve a Mach number of 1. If that happens at all, that's not necessarily the point. And then here we have an exit of our nozzle. Over the exit here, we will then have a velocity, u exit. I will have a pressure exit. I will have a temperature, density, speed of sound exit, whatever. And then the flow continues from the reservoir past the exit, and then I have another reservoir over here. Reservoir, just go out where we have, say, standard atmospheric pressure, for instance. Something like that. And now comes the clue. The driving force for this problem will now be the pressure difference. You have a P0 in this reservoir, and then you have an atmospheric pressure here as a reference. The difference there, he's going to decide the outcome, the geometry, the physics, what's going to happen. So that is sort of the critical parameters that we can sort of play around with. Whatever this pressure at the exit is going to be, that's something we have to look into. That's something we have to look into. Okay. First of all, when it's subsonic, Mach number smaller than 1. That one is rather boring, actually. What's going to happen? Well, you have an opening. The flow goes out here. And at the exit here, the opening, the pressure exit is just going to be equal the atmospheric pressure. And then the jet here, he will go into this open reservoir. So no problem there. Of course, depending on the Mach number, smaller than 1, but maybe it's bigger than 0.3. So yeah, we have some compressible effects here, meaning you can have a change in temperature, you can have a change in density, speed of sound actually also. So, but the pressure there sort of have to match. So that's not so so interesting. But when you go to supersonic, that's more interesting. Bigger than 1, thank you. Then a lot of things is going to happen, or may happen. So here you have the opening, and then you have a pressure at the exit here. And that one is going to be now quite different than whatever we have at our end reservoir. They are going to change a lot. We have 3 possibilities. You can have the same as actually a subsonic situation. Exit pressure equals the atmospheric pressure. That can happen. It all depends on the global driving force, the difference between these 2 pressures, P0 and P atmosphere. Then we can have the situation where this exit pressure is actually bigger than the atmospheric pressure. Then what's going to happen? You're going to get some expansion waves. Well, what should we write here? Same as subsonic. Here you will get, don't they have any decent chalk? Then you will here have expansion waves. So they may look something like this. So then you have a rapid change here in pressure, density, temperature, everything over the expansion waves. And then finally, this exit pressure may be lower than the right reservoir pressure. And then you will have shock waves. Shock waves. So yes, we are then going to need a sudden jump in pressure over a shock wave. So we will have some shock wave structures on the outlet here. Okay, so how far can we go with our theory? Well, we can go from the reservoir to this narrow cross-section where you have Mach 1. But we can't really by hand do the calculations what's going to happen through shock waves, expansion waves. That is not possible. Typically you will use then tables. You have some formulas that can be interpolated, but tricky. So what is a bit strange with this supersonic situation, just remember, you sort of have an unsymmetric solution. Of course here, starting from the reservoir, and then the velocity here definitely has to increase because the cross-sectional area becomes smaller and smaller. And in this region, then with a supersonic situation, even though the cross-sectional area is increasing, the velocity is also increasing. That's a weird thing, but that's actually going to happen, or it may happen, depending again on the total driving force. So let us clean this one. No questions so far. That's okay. This also means In the upcoming exercise 8, where we are going to simulate this, then of course I want to have a look at the 3 different possibilities here. So that's something you have to be prepared for. So, yeah, we can redraw this one. So we have a driving force, P0, and then over here somewhere atmospheric pressure. And yes, we have a velocity u here. And this velocity, if you sort of change the driving force or increase the driving force, it will go faster and faster until you will have Mach number 1 here. So that is sort of the maximum. And when that happens, m equals 1 in this cross-sectional area, AM. When that happens, we say this nozzle is choked. Choked nozzle. It means you can sort of lower that one even more to see if you can get more flow through this nozzle, but no, you can't. It really doesn't matter. The mass flow of the gas through this nozzle is given. You can try to use even greater driving force. You will have the same mass flow through this cross-sectional area, whatever you do, doesn't matter. What's going to change then is the situation here at the exit, whether you get shock waves, expansion waves, or not. But when it's choked, you can't obtain any more mass flow. So let's now have that one. The maximum mass flow, max mass flow, say for Mach number equals 1, or should we call it m dot star? Yeah, why not? And that one is now given from our relations. We had the density star when it's choked, we had the velocity star choked, and then even the area multiplied, thank you, area, and the area is of course our AM. Should be an A here, like that. And then of course the velocity, that one is the same as the speed of sound at the critical value there, of course. So that one is given, and yeah, it can actually be calculated. Should then be the same as the area, and then you will have the situation in your reservoir, density, speed of sound, and then if you calculate it, you multiply with 0.579 or something like that for air. Then it's choked. So this is the maximum what you can achieve, no matter what you do. Really doesn't matter. Okay, then we are missing a little bit, but I'm not sure I want to have a look at all this now. No, I think I'll wait with the rest of the theory then for next week. Conclusion, yes, we can use our simple equations until we have reached the most narrow opening. And we can have an idea on what's going to happen on the other side, but remember our equation system then is not valid anymore, because over a shock then all things changes and the enthalpy is going to increase, and it's not reversible anymore, it's irreversible. So our theory breaks down, and then we have to rely on maybe some gas dynamic tables and stuff like that for Mach numbers bigger than 1. Or we do a CFD simulation of it, of course. So that is what we are aiming for. Let's see. Yeah, no, I think actually I will stop there. It's a good place to stop. So I will continue then next week, a little bit more about what might happen when we have these 3 situations. Any questions? Okay, but then we stop here.